Hello, everybody. So I am Karima Meghar from Cirad. Today I will present you the methodology for the estimation of repeatability and representativeness of NIRS and hyperspectral imaging measurement. So this is the main steps we have to follow to reach the steps of development of method of analysis on NIRS. All the experiments that I will present here were carried out in IITA Nigeria during my mission in December 2021. And the contributors in this presentation are Fabrice W from Cirad and Michael Adeshekan, Shegan Fawal and Emmanuel Alamou from IITA. Okay. And the outline of this presentation will be in three parts. The first part is the measurement and the determination of instrumental noise and the repeatability of spectral measurement. And the second part will be dedicated to the measurement and the determination of representativeness of hyperspectral measurement. Here we will take a case of fresh lamp, and the third part will be dedicated and the third and last part will be dedicated in the calibration for spectral prediction of quality attribute. Here I will show you the case of trimatter in lamp. So for the instrumental noise and repeatability of spectral measurements, for the first step, the protocol of measurement of spectral noise that we have done. So we take 10 hyperspectral images of white reference consecutively in the repeatability condition using a speaking FX17 camera from IITA Nigeria. And here, as you can see, here is the white reference, is the spectrum, and white reference has the 100% of reflectance. And then we calculate for each image, we calculate mean spectra of each image. And here you see the mean spectra of each image of white reference. And then we will estimate from this spectrum, we will estimate the dispersion between each spectrum and the average spectrum by the root mean square error, RMS calculation. And the formula for the calculation of RMS is there. And RMS is like standard deviation, but it is for spectrum and for multivariate data. Okay. So from this statistic parameter, we calculate the difference between each spectrum and the average spectrum of the 10 spectra. Okay? And then when we do that, the next step is the recalculation of the determination of spectral noise. Here you have the mean spectra of white reference. So we take 10 repetition, we have 10 spectra. This is just the instrumental noise of our camera, of our X17 camera. And here, as you can see, we have a random evolution of spectra as we can expect it. And from this, we can see in the extreme of spectral range, we see the high instrumental noise. Okay, and here from this spectra of instrumental noise, we apply RMS and to see the difference between each spectra, average spectra, and then here the right. you see here in this plot, you see the RMS value of each mean spectra. So we have 10 and we have 10 values of RMS. And that mean this is the RMS of instrumental noise of our instrument camera, which is the camera. And here, from this plot, we can see that the RMS of instrumental noise is randomly distributed between RMS mean in the represented here in the red line, and the RMS mean and the plus minus true standard deviation here represented here in green dashed line. So here we can from this we can calculate that our confident interval is between 89 to 923 microreflectance with the error threshold of 5%. So we can, from here, we can say that the instrumental noise of this camera is a mean RMS, which is 506 microreflectance. Okay, and for the next step, we can also, from this data, we can also check the repeatability of spectral measurements. We use the same data, so we use the RMS values of each spectra of white reference. Here you have the value of each one, RMS. So from here we can estimate and determination of repeatability by using this formula. So the repeatability of our spectral measurement using this instrument is equal to RMS mean is 506 microreflectance plus minus T alpha per standard deviation divided by root freedom, degree of freedom. Okay, and we have here RMS mean that is like previous, the same one. This is the RMS mean here is our instrumental noise, and standard deviation, calculate also from this data standard deviation. And N is the number of repetition. In our case, we take 10 repetition on white reference. And alpha is the error, threshold error, which is 5%. And T alpha is the critical point on of probability at this 5% and at error threshold of 5%. So we found our repeatability of this spectral measurement using the FX17 camera, which is 506 plus minus 127 microreflectance. So from this work, we can see that the limit of repeatability of hyperspectral measurement using IHVA speaking FX17 camera is from 379 to 639 microreflectance. So if we find the RMS value between this range, confident interval, we can consider this is the repeatability of noise. Okay, and the repeatability of spectral measurement could be also calculated from spectral acquirement on the stable sample, not only from white reference. So stable sample means no variation in composition over time. Okay. And the second second important step we have to check before to go to the development of calibration or to try to do something. So it is the representativeness of spectral measurement on fresh yam. In our case, we take fresh yam, and we take also the case of hyperspectral imaging. But this step, we can apply also the step for other spectral measurements, NIRS, and all the spectral measurement. Okay, so in our case, we use hyperspectral imaging. Okay. So for the sample for this, we follow for the sample preparation and the protocol of measurement. So to check the representativeness, we take two contrasting genotype of yam, and then we choose 3 tubers, small, medium, and big for each genotype. So you can see here in this picture, we take 3 sizes of tubers, and then from here we take 3 slices, proximal, central, and distal, were divided from each tuber, like here. From each tuber, we divide 3 slices on proximal, central, and distal. And then we take one hyperspectral image on each face of each slices, each face of each. That is mean we take one here and one here. And dry matter, we take also, we measure also dry matter on this each slice 2 times in 2 repetitions. Okay, we 2 replicate, and using this this camera, as you can see, the number of samples that we produce from this experiment. So for hyperspectral imaging, so we use 2 genotypes per 3 tubers, per 3 slices or zones, or per 2 images, we have 36 images. And for dry matter, we have also 2 genotypes for 3 tubers, for 3 slices, zones, per 2 repetition, because each slice we do 2 repetition, 2 values of dry matter. Okay, so we have 36 dry matter values. So for the determination of spectral representativeness of hyperspectral measurements, so we take here mean spectra, we calculate the mean spectra of images. So here you can see the mean spectra of images, but only of one genotype. We don't use all the, so we use only all the spectra of one genotype. So we have 18 spectra. And from this spectra, we apply RMS to see a spectral variability between tubers, because we use, as we said, we use 3 tubers per genotype. And then we apply also RMS to see, spectral variability within tubers, inside tuber. Okay. So as we said, that we have the proximal, central, and distal zones for each tuber. Okay. And here in the left, you see this plot. From this, you see the spectral variability. We see the RMS values by tubers. Okay, obtained by tubers. Here is the, in red dashed, you have the total average RMS, and here in column you have RMS, average RMS, but for each tuber. And here you have the values of each samples on tubers. So from here you can see that the average for each tubers, average RMS of each tubers, as close to the RMS, the total mean RMS, so the total average RMS. And we see also that the variability on the big tubers here, big, M, and small, big, medium, and small, as higher than the others. And in small, we see the low variability. spectral variability. Okay, and here in the right, this is the RMS values by zones. So here central, distal, and proximal. And as you can see here, we see that the RMS values by zones for central and distal as close to each together. So they are close together, and also close to the total mean, the total average RMS. And also here we see that there is some difference between central and distal, between central proximal and distal central. So see, the next, what we do after this, we to see if we have significant difference between tubers or significant difference between the zones inside tubers, we apply of each of the RMS values the Fisher statistical test, which is the Fisher test, F-test. Okay, so what we see, but for the variability between tubers here, we find that there are no significant difference between tubers of the same genotype. No significant difference in spectral difference. Okay, I see that spectral, not biochemical and physical. Okay. This is because we find that the pure value is higher than the error threshold of 5%. Okay, and here also for this variability within inside tuber or within tuber, we found that significant difference between we found the significant difference between proximal and distal, because p-value is lower than 5%, error threshold error 5%, and also a significant difference between proximal and distal. Okay. But we don't. We find no significant difference between central and distal, and we see that in this plot. We see that is that this RMS is close to each together. Okay, and from that is meant that we have here in the case of hyperspectral measurement of fresh yarn, we say that we find that spectral variability inside tuber as higher than spectral variability between tubers. Okay, and for the third step, when we do the first and the second step, we can go to the third important step, which is calibration for spectral prediction. Here, we take a case of prediction of dry matter on fresh slices of yarn. So we do tentative calibration for prediction of dry matter by hyperspectral imaging. Why tentative? Because it's not for calibration for the prediction on routing. This is just the calibration to demonstrate the capability of this technique to predict dry matter in fresh yarn. Okay, so we take the 36 images that we acquired on the 2 genotype, like I showed you before. And then we also calculate 36 mean spectra. Okay, and for this, from this 36, we apply PCA principal component analysis to the mean spectra. Okay, and then we apply also the partially square regression of the 36 mean spectra and the 36 values of dry matter. So here in the left, we see that we see PCA score plots in PC1 and PC2, two first axes, and we see here along the PC2 with 11% of explained that we see the difference between two genotypes, genotype 2 in green and genotype 1 in red. So we can discriminate between them using this hyperspectral measurement. Okay. And here also we also try the PDLS model for prediction of dry matter by hyperspectral imaging. So this is the model. So we have the predicted dry matter by hyperspectral imaging here, and in function of laboratory measurement dry matter. So the dry matter measured in laboratory. Okay, as you can see here, we have a good performance of this of the prediction of dry matter with the coefficient of determination of 0.93 and error of prediction of 0.74, okay, 75. Okay, and from this result, we can see that hyperspectral imaging could be used for discrimination between contrasting genotype of young, okay, and also for prediction of dry matter with a good performance. Because we can use hyperspectral imaging to predict dry matter with good performance. So we can go ahead and use more samples and use more varieties and so on. Okay. And also, I want just to show you some images. So images for this is the hyperspectral images projected on SCORE PC1 of PCA. So this is the images of genotype 1 and the images of genotype 2. So we have, as I said, that we take one image of each case. So that is why we have the true sample. As you can see, the red is the high water and the blue hard is low water. Present low water, and here, as you can from this image, we can visualize the difference between two genotypes. You can difference between them. So if you can see here that for genotype 1 we have more red, so we have maybe more water, and for the genotype 2, for all slices, we have more. So we can also, hyperspectral imaging can be used also for the visualization of from two contrast difference of from two contrasting genotype. Okay. So for the conclusions, and the steps that we do. Hyperspectral measurement.
Karima.
For the good, yes.
Yes, we have a cut in the demonstration. You can begin now for the conclusion.
Yeah, I'm in conclusion. Okay.
Okay.
So for the conclusion, just to remind, for the good development of methods for spectral analysis, NIRS, visible or just NIRS or hyperspectral measurement. So we have to follow some required steps. So first of all, we have to check instrumental noise before to start anything. Okay, and then if the instrumental noise is okay, we can go to check the limit of repeatability of spectral measurement, and also we have to check representativeness of spectral measurement to identify the number of samples to take per examples per tubers, number of tubers per genotype. Okay, this is very useful to do this step to determine this okay, and then we have also to check the capacity of spectral measurement for the discrimination between contrasting samples. Okay, So as I show you that with hyperspectral, we can see, we can visualize, and also we can discriminate between two contrasting samples. And we, in the end, when we can demonstrate, also we have to demonstrate the good or bad prediction of target component by spectral measurement. Okay. Thank you for your attention.
Thank you very much, Karima. Nice presentation. Now we have to do hyperspectral analysis. You need to be first a good statistician. And
yes, not only hyperspectral, all spectral measurement, and also for laboratory.
Yes. Yes, I have many questions in the chat. We'll take first. Why 10 measurements made or not at 30 or 40? Is it the number of measurements related to the noise measured? Because why did you decide 10 and not why 20 or 30? Or...
No, we take just 10. I don't know, but you can take 6 or 10. But not choose to take 10 to be. Huh?
Any reason for the 10, or it's
no reason, no. Just we normally take between 6 and 10.
Okay. Then at what point do you consider that the noise of the equipment is too high and that is no longer within the standards?
So yes, we have the limits. Yes,
Normally you should have with the instrument from the manufacturer of the instrument, you should have the limit of the instrumental noise. In this case of hyperspectral imaging, we don't have this, so we can do it as Karima has done with the reference measurement, and we can check it every time we use the instrument. You just have to check by 5 or 10 spectra. The number of spectra to do the measurement noise 10 is enough. To do the measurement of the noise of the instrument, 10 spectra is enough to do that. When you do for a sample, we are not looking to do a lot of spectra from the same sample. So we need to define the optimum number of spectra to do for one sample. And to have an optimal number of spectra, it means that you need to first know the repeatability of the measurement, and second, know the variability of your product to be able to catch the entire property of your product. So that's what we have done in this little experience, just to show this, to highlight how to do it. So it's a procedure to start a new, when you start with a new product, you have to do like this, to know how many measurements you have to do for your product.
Okay, thank you. From Thierry Tran. Maybe Thierry, you ask your question, or the question is how to calculate the average spectra of 10 images in the white reference. Do you define a specific area of each image and first calculate?
What is the question? How to calculate?
How to calculate the average spectra of 10 images.
So we calculate the average of each image. So this is for the white reference. We take an image, and you, as you know that in the image, each pixel is one spectrum. Okay. And that is why we calculate mean spectra, just to have just one spectrum per image. Okay. Do you define specific area of each? Yes, we define the area of each image. Yes, we take
so for example,
we do segmentation. We do segmentation in the image. Okay.
So for example, how many pixels do you take from each image?
Yeah, we take all the image. We take all the image, and we segment, and we
all the image.
All the image. Okay. Yes.
But the image is not only the white reference. You have also
we take
the white reference.
Yes. Okay. We take image mean spectra on only the reference. So we do segmentation before. Okay. We choose the region of interest before to do the mean spectra. Okay.
Yeah. Okay.
Only in the image, we see only the reference.
Okay. And then in that region of interest, typically how many spectra, how many pixels do you have?
We have more than we have more than 30,000.
30,000. Okay.
Wow.
That's why it's so big.
That is why we take just the average spectra, and if you use the classical NIRS, you take just one spectrum. You can use it for the calculation. But in my case, so I use hyperspectral. I can't take all the pixels, all the spectrum in the image, which is why I prefer just one. Okay?
Yeah. Okay.
Thierry, you have the floor. You have another question.
Yeah. Well, I think I misunderstood the slide that Karima was showing. Fabrice gave some answers in the discussion. It's like it was. I think the next slide, Karima, if you can move forward. It seems that no, another one. Wait, further.
Next one.
Yeah, this one. Because, okay, just looking from not being specialist on the statistical treatment, the differences in the graph on the right seems much less than on the left. But then you said that there are no statistical differences on the left.
Yes,
and there is a statistical differences on the right. So I was a bit surprised to see
Yes,
that.
me too. But when I do Fisher statistical here, I find that no significant difference between, because I compare the variance. Okay, with Fisher test, we compare the variance between this and this and between this and this. Okay.
Yeah. Okay. So those bars, they don't show the. I'm not sure how to call it, the actual la grandeur. They don't show the value, but the variance of the value or something like that.
Okay.
Yeah.
Yes. Okay. And here, okay. Another question. How to calculate? Hi, everyone.
Are you okay, Thierry?
Yes, well, I need to do some reading on the statistical analysis of differences.
You have
but still,
question about
compared to cassava. In the case of cassava, we can see a lot of differences between different tubers.
In this
and
case, I don't
much less differences within the tubers.
Yeah. In this case, for yam, I don't see the difference, very big difference between tubers. Even so, when we see the dry matter values, it's the same. Okay, I think we see that the inside tuber have big high variability in tuber.
From Didier and Thierry, the same question about
this case.
There is two questions, one from Thierry, one from Didier. Absence of variability between tuber from the same genotype observed, whatever the part of the tuber analyzed. Now the proximal is different, no?
Yes.
And for Thierry, the mean of the proximal central distal parts seem much closer to each other.
Yes, this one is for Thierry. Can you repeat the question from Didier?
Yeah, you're there. Can you ask your question? Didier say absence of variability between tubers for the same genotype of
C'est pas absence, il n'y a pas de, c'est not absence, but not very significant difference between the three tubers. Not absence.
Okay.
Variability, but not significant.
Okay, is it observed in all the paths of the tuber?
The type of the tuber, yes, because we compare, here, we compare
what we
between
observe is
parts. Huh? What is the question? Because
hello, Didi.
if you can see big and small, we compare the values also by zones. For example, here we compare
okay.
this one. I will say this one is for proximal, for example, and this one also proximal. Okay.
Okay, okay. I understand that the same result, whatever of the tuber. There is no significant difference.
We mute your mic. Edwin. More question to Karima. I want to give the floor also to Michael and Alamu who participate to the trial. Maybe they have some comments, some question. Michael?
Yes. Good afternoon, everyone.
Good afternoon.
Yeah, thank you, Dominic. Well, Karima, thank and well done for the great presentation. And it was such a very nice time together in Nigeria to work on this. I think Karima has done justice to the work, and some of the findings with not finding variability within between the different sections of the tuber. But what I really wanted to say was some of our observation during the measurement was the shape of tuber tends to affect some of the resolution of the image, the shape of the tuber. In the process of selecting the region of interest, we discovered that if the tuber shape is not completely regular, then it tends to affect the selection and segmentation of the image to pick the region of interest. So tuber shape seems to be to contribute an important effect to the image. So we try to work around getting a tuber with a regular shape and to be able to cut out a shape that gives a continuous and consistent image. Thank you. I think that's my contribution for now. Thank you.
And Michael, are you using the hyperspectral at the moment in ITA?
Yes, we are. Yes, we are using it now.
Okay, on YAM or on cassava?
Currently on YAM. Currently on YAM.
You have some harvest at the moment. This is good. Maybe, yes, Emmanuel, do you have something to clarify? You were part of the team.
Yeah, thank you, Karima. Thank you, Michael. Are you hearing me?
Yes.
Okay, yeah. Thank you very much. It's a great work, and we still need to continue with this. That observation actually. We discussed about it, and what we observe is between tubers, no difference, but within the same tuber, proximal, central, the central and the distal, no difference, but central and distal, both of them are different from the proximal, which is expected because the head, the dry matter of the head is higher than both of the distal and the central. Actually, what we are planning to do is to increase the number of variety we use. We use just one. We want to increase to 3 and see if this follow the same pattern. And we can report about this, but this one has given us a good knowledge how to set up the representativeness of the spectral measurement, as well as some repeatability tests. So this one is being established, and then it is setting us a lot. Then we can extend this to cassava. This is not the season for the harvest for cassava, but we expect that we can extend it to cassava when we perfect that of yam. At least they are always related. Then there's another thing we want us to look as well, which we are still going to look. We look at it, but it's not been reported yet by Karima here, is the using longitudinal. This one is centric. The one we reported here is the centric from each section. But what about the longitudinal? So we still want to exploit that. So thank you so much. Thank you, Karima, for good work. And we thank.
Yes, I have just a complementary question. Are you planning to correlate with cooked product, with processed product? Because at the moment, this is only on raw sugars. Are you planning to do some kind of experiment as Karima was doing last month in Colombia?
Yes.
With a raw and cooked product. Alamu is for you, the question, or Michael.
Yeah, thank you, Dominic. Yes, what part of what we plan to do is whatever we are doing on the fresh material, we take it onto the product, the cooked product. So we agreed on certain steps to collect both image and spectra of boiled yam, for instance. So the same image we collected for raw, we are taking the same image on the fresh products. I mean, on the cooked product. Okay. So with intention of trying if we are able to establish relationship between the image from the raw and the data from the cooked material. So currently we are also collecting a spectral, image on the boiled yam. So as Dr. Alamu said, also we are also going to explore that on cassava during cassava harvesting. Thank you.
Very good. Thank you very much. Any more questions to Karima before closing? Any questions?
Well, Karima, I have a question for you.
Good.
Yes.
Yes.
When are you going back?
Software. So you will ask me. I know you will ask me about software.
You know what my question is. So maybe you take it up. I know during the after the training we had some review and things we needed to follow up. The MATLAB software, which is very key to the processing of the image.
Yes, or
yes.
Python.
So what's the plan on that?
So we, I see that with Python also we can do the image processing and easily, and there are some very useful packages in the internet. So we have you have Python. It is a free software, okay? And this one you can do this one like you can do with the MATLAB, okay? So I am working now with Denis Cornet to try to translate my script from MATLAB to Python, and then I can give you this. But you have also to try to train on Python, okay?
Thank you
Python
for that.
Python is like R, but with Python you can do the image processing, and there are very useful packages to do that. And Python, it is free. You don't need to buy licensing. Okay.
Okay, we need to go now, and
maybe we have solution for you.
You will discuss together after the webinar.
Yes, this is
a big thank you, Karima, for this presentation.